In this video, we will look at sets and disjoint sets. Let us define a set. A set is a collection of elements. We can also say that a set is a collection of elements having some common features. For example, let us consider a set S consisting of 10 elements from 1 to 10. An important property of sets is that all the elements of the set are distinct or unique. That is, a set will not contain duplicate elements. So, if you observe, the set S has all the elements which are unique. In design and analysis of algorithms, we assume that the elements of the set are always numbered from 1 to n. Now, coming to disjoint sets, this set S can be partitioned into three different disjoint sets. Let us call the first disjoint set as S1 with the elements 1, 7, 8, and 9. Let us call the second disjoint set as S2 with the elements 2, 5, and 10. And let us call the third disjoint set as S3 with the elements 3, 4, and 6. These sets S1, S2, and S3 are called as disjoint sets because none of these sets S1, S2, or S3 have a common element. What this means is that disjoint sets will not have repeated elements. So, if you observe, the element 7 is present in disjoint set S1 and is not there in disjoint set S2 or S3. In the same way, if we consider element 5, it is only present in disjoint set S2 and is not there in disjoint set S1 or S3. So, if you look at any element of set S, it is present only in one of the disjoint sets. The other point is that mathematically, intersection of disjoint sets will be null. In this case, S1 intersection S2 is null because there are no common elements. In the same way, intersection of S1 and S3 is null because there are no common elements, as well as the intersection of S2 and S3 is also null because there are no common elements. So, we call these three sets S1, S2, and S3 as disjoint sets. Another property of sets is that they are not ordered. What this means is that set S1 consisting of elements 1, 7, 8, and 9 is the same as the set consisting of elements 7, 1, 9, and 8 because the elements are same but arranged in different order. So, the order of the elements in the set does not matter. In the same way, the set S2 consisting of the elements 2, 5, and 10 is the same as the set consisting of the elements 10, 5, and 2, or is same as the set consisting of the elements 5, 2, and 10, because the elements are same but arranged in different order. So, the elements of the set are not ordered. That is, the order of the elements in the set does not matter. And if the elements are same, then the sets are considered to be same. Now let us look at how disjoint sets are graphically represented. Each disjoint set is represented as a tree. One possible representation of disjoint set S1 is to have element 1 as the root and all the other elements, that is element 7, element 8, and element 9 as its children. If you observe, the important point here is the links in the tree are from children to its parent, or in this case to the root. This is different from the traditional parent-child relationship in a tree where we have links from parent to its children. So always remember, when we represent a set as a tree, the links will be from children to its parent. Now this representation of disjoint set S1 as a tree is one of the possible representation of set S1. We can have any element as the root. It does not matter. For example, we can also consider element 7 as the root and all the other elements, that is element 1, element 8, and element 9 as its children. This is also one of the possible representations of disjoint set S1 because, as said earlier, sets are not ordered. So we can consider any element of the set as the root and make all the other elements as its children. Anyways, let us consider the first representation with element 1 as the root for the disjoint set S1. In the same way, one of the possible representations of disjoint set S2 is to have element 5 as the root and all the other elements, that is element 2 and element 10, as its children. And for the disjoint set S3, one of the possible representations is to have element 3 as the root and all the other elements, that is element 4 and element 6, as its children. So this is how we can graphically represent disjoint sets as trees. Now, using this representation, we can identify the disjoint sets just by the root of the trees representing them. That is, disjoint set S1 can be identified by the root of the tree whose element is 1. The disjoint set S2 can be identified by the root of the tree whose element is 5. And the disjoint set S3 can be identified by the root of the tree whose element is 3. Now, apart from this, we can maintain a pointer to the root of the tree representing the disjoint sets. So, we will have a table with the disjoint set name and pointers. For example, we will have a disjoint set name S1 and have a pointer to the root of the tree representing S1. That is a pointer to the tree with root element as 1. In the same way, we will have disjoint set S2 and have a pointer to the root of the tree representing S2. That is a pointer to the tree with root element 5. And similarly, we will have disjoint set S3 and have a pointer to the root of the tree representing S3, that is a pointer to the tree with root element 3. So this is how we can represent disjoint sets using trees and maintain a table with the disjoint set names and the pointers to the root nodes of the respective trees. Now, to simplify the operations that can be performed on disjoint sets, we need to represent the nodes of the tree using an array of elements. It is very convenient to use arrays since the elements of the set are assumed to be numbers or integers. Now, since the total number of elements in three disjoint sets, S1, S2, and S3 are 10, so let us consider an array of 10 elements. Let us call this array as P, where P in this case stands for parent. And since we are using arrays, it is very easy to represent the node of the tree using index of the array. Therefore, let us have I as the index of the array and all the indices of the elements within brackets. So here, index 1 of the array P represents the node of the tree with element 1. In the same way, index 2 of the tree will represent node 2 of the tree and so on. That is, the ith index of the array represents the node of the tree that contains the element I. Now, when we have array P, let us look at how the disjoint sets are stored in array P. If the node is a root node, then we will store -1 at the ith index of the array, where I is the element in the root node. If the node is any other node and not a root node, then we will store element in the parent node at the ith index of the array, where I is the element in the node. So let us look at how to store the disjoint set S1 in the array. The root of the disjoint set S1 is element 1. Therefore, we will store -1 at index 1 in the array since element 1 is the root node. Then we have the node with element 7. And since the node with element 7 is not the root node and its parent is node with element 1, therefore, we will store 1 at index 7 in the array. That is, we are storing the parent, which is 1 of the element 7 at index 7 in the array. Then we have the node with element 8. And since the node with element 8 is not a root node and its parent is node with element 1, therefore, we will store 1 at index 8 in the array. That is, we are storing the parent, which is 1 of element 8 at index 8 in the array. In the same way, we have the node with element 9. And since the node with element 9 is not a root node, and its parent is node with element 1, therefore, we will store 1 at index 9 in the array. That is, we are storing the parent, which is 1 of the element 9 at index 9 in the array. So this is how we can store the disjoint set S1 in the array. Now let us look at how to store the disjoint set S2 in the array. The root of the disjoint set S2 is the element 5. Therefore, we will store -1 at the index 5 in the array since element 5 is the root node. Then we have the node with element 2. And since the node with element 2 is not a root node and its parent is node with element 5, therefore, we will store 5 at the index 2 in the array. That is, we are storing parent which is 5 of the element 2 at index 2 in the array. In the same way, we have node with element 10. And since the node with element 10 is not a root node and its parent is node with element 5, therefore, we will store 5 at index 10 in the array. That is, we are storing the parent, which is 5 of the element 10 at index 10 in the array. So this is how we can store the disjoint set S2 in the array. Now let us look at how to store the disjoint set S3 in the array. The root of the disjoint set S3 is element 3. Therefore, we will store -1 at index 3 in the array since element 3 is the root node. Then we have the node with element 4. And since the node with element 4 is not a root node and its parent is node with element 3, therefore, we will store 3 at index 4 in the array. That is, we are storing the parent, which is 3, of the element 4 at index 4 in the array. In the same way, we have the node with element 6, and since the node with element 6 is not a root node and its parent is node with element 3, therefore, we will store 3 at index 6 in the array. That is, we are storing the parent, which is 3 of the element 6 at index 6 in the array. So this is how we can store the disjoint set S3 in the array. And this is how we can represent all the elements of the disjoint set in array P, which simplifies the operations that can be performed on disjoint sets.